Well, good morning, everybody. Thank you so much for joining us today. My name is Stephen Zoff, and I'm the director of the HASS COE, the Highly Automated System Safety Center of Excellence. Welcome to our Quantum Technologies 101 webinar. This series is presented by the HASS COE and ARPA-I, both of which are based in the United States Department of Transportation Office of the Assistant Secretary for Research and Technology. So good morning, everybody. So this webinar, which is co-hosted by HASS COE and ARPA-I, will provide a highly informative and engaging overview of emerging quantum technologies and how they can revolutionize the transportation industry. And our goal today is to introduce the full scope of quantum technologies and really start a conversation about how these technologies can address challenges within the transportation domain. So please join me in welcoming our moderators, Dr. Dan Lemaster, who is a senior scientist at the HASS COE, and Prachi Vakkaria, who is strategic advisor for innovation and ecosystems at ARPA-I. Thank you so much. Prachi, take it away.
Perfect. Thank you, Stephen. We're really excited to have both Will and Paula here today. To tell you more about them, I'll hand it off to actually Dan. But very excited to have you here today. What we'll have our presentation from Dr. Will Oliver, later Dr. Paola as well. And from there, we'll have about 15 to 20 minutes at the end for Q&A and discussion time of applications you see in the quantum sector. So please keep your questions and ideas ready.
All right, thank you, Prachi. Yeah, thank you. I'm Dan Lemaster, as you heard, from the Highly Automated System Safety Center of Excellence. You met Prachi as well, and we are kindred spirits in our enthusiasm for quantum technology. But let me say that Prachi is most completely responsible for why we are here today, why we have these amazing speakers, and why we'll have even more at our workshop on July 10th. So please do join us for that as well. Prachi's ability to organize and to attract this kind of talent is to our cause is exemplary. So I wanted to say thanks to Prachi and make sure that you all know that it is primarily Prachi you have to thank, and I am very happy to be here to help out. And now, if I may, I will tell you where our enthusiasm comes from. The quantum technologies that you'll hear about today are gaining momentum, and already quantum computers are being applied to problems in like port optimization, congestion mitigation, battery chemistry, and aviation manufacturing, and also for quantum sensors. They may change what we think is possible in terms of navigation, surveying, communications, and infrastructure. And I want you all to think about last year sort of as a watershed moment for AI and how that has changed what we're being asked to do in the US DOT and how we think about our job. There won't be too far in the future where we are going to have this same watershed moment for quantum technologies, and we can be ready. And we'll start today in that preparation with the speakers that we have here. Thank you both, and I'd like to hand it back over to Prachi to introduce our first speaker.
Perfect. So Dr. Will Oliver will go first. He'll tell you a little bit more about quantum computing, what that means, and where is the sector today. So Dr. Will Oliver, he's the director for the Center for Quantum Engineering at MIT. He's really a pioneer in this field and has one of the most excellent labs in the country in this domain. So Will, over to you.
Great. Thank you so much, Prachi, for the introduction. I appreciate it. Let me bring my slides up. So it's really a pleasure to be here today, and I'd like to talk about quantum computing. So without further ado, we're entering a second quantum revolution. I'll talk in a moment about what that means, but it's a revolution where we're going to have advanced sensing, communication and networking, and information processing or computing. We call this quantum 2.0. And quantum 2.0 utilizes quantum mechanics to sense, communicate, and process information in ways that are either practically prohibitive or unobtainable by conventional means. And I'm going to talk about quantum computing specifically, and then Paola's going to talk a bit more about quantum sensing. So before we get into quantum, I think it's useful to go back and look at the history of classical electronic computing. In the early 1900s, we invented a vacuum tube. It was a 3-terminal device, and it was used for amplifiers for radios, basically, for a number of years. And it wasn't until 1946 that it found its way into a computer that we've all probably heard of called ENIAC. That was 1946, University of Pennsylvania. This computer took up a whole room, wasn't very powerful, but it did a few useful tasks at the time. The following year, the transistor was invented, also a 3-terminal device, but now based on semiconductors. And within about 10 years.
Sorry, quick interruption, Will. We don't see your slides moving.
You don't see the slides moving?
No.
I see.
They're still on the presentation slide, on the first slide.
Yes.
I don't actually see the slides at all.
Yeah, they're usually nice.
Okay. I'm not sure what's going on. All right, let me try one more time.
Yes.
And then stop sharing. It's very strange because we just did this right before and it all worked, right?
Yes.
All right, let me try again. Try this one. All right, duplicate. Okay, are you seeing it now?
Yes, and now advance the slides. Let's check.
Yeah. Let me. Okay, so did that advance?
Yes, perfect.
All right.
Please
I don't
continue.
know what's going on.
Yes.
It's these classical computers. We need quantum computers to make this work. Okay, so what I was saying is that the computing development, started in the early 1900s. I think we got up to this TX0, which was the first transistor-based computer, but it didn't look anything like the processors we have today. This also took up a whole room, but it was basically these 3-terminal devices soldered together. Okay, so to get closer to the chips we know and are using right now, we needed the integrated circuit. That was the late 50s, but it still wasn't until the 70s that we actually saw a chip like this Intel 4004, a 4-bit processor, 2,000 transistors. And then another 25 years to get the Pentium Pro with millions of transistors, and another 25 years to get to where we are today. Multi-core processors, billions of transistors, graphical processing units, and more. And in fact, now chips have more than 100 billion transistors on a single chip. But these are wonderful, but we have to remember it took us over 100 years to get here. Now, quantum computing is much newer. It's nascent. In the early 80s, people like Richard Feynman said, look, if you want to build, or if you want to simulate a quantum system, you should build another quantum system to emulate it, okay? And people thought about what that meant, and 15 years later, we started to see algorithms that could use a quantum computer if we could possibly build it. And some of the most famous ones are Peter Shor's algorithm for cryptanalysis, but also quantum annealing, adiabatic quantum computing, Grover's algorithm, etc. And here we are 25-ish years later, maybe even 30 years later now, and we have the first demonstrations of quantum error correction, small-scale quantum computers in the cloud. You can actually use them, and it's a very exciting time. So the takeaway is this: quantum computing is real, first of all. It's happening right now. We call it quantum 2.0. As opposed to the quantum 1.0, which was the foundation for our present information and economic security. What I mean by that is the transistor, to understand how that operated, we needed quantum mechanics. But that transistor is just a faucet. It's an on-off switch. It's completely classical. That's quantum 1.0. Quantum 2.0 is we now use the quantum mechanics as the switch, right? And that holds the promise to similarly impact this century. We also know that advancing from discovery to useful machines takes time, takes engineering. And the last point is you got to be in the game to play. And what I mean by that is it's no wonder that the companies that are making these very complicated chips with billions of transistors, they didn't jump in 2000 or 2010. They were in it for the long haul. Okay. One slide on qubits. Qubits come in basically two different flavors. One is the atoms that you'll find in a periodic table, and these atoms have different behaviors depending on whether the number of protons, neutrons, or electrons that they have. And we'll look at some of these atom-based computers in a moment. The other type we call artificial atoms. These are basically just electrical circuits. made from inductors, capacitors, and Josephson junctions. And you can arrange them into circuits that are basically resonators. And then they look and behave a lot like natural atoms. And there's even a whole family of them. This is just a few of them here. You could think of this as a Mendeleev table of artificial atoms. So quantum technologies are based on either the natural atoms that we get from nature or the circuits that we can build that mimic atomic properties, either one. So then you can ask, how is a quantum computer different? Well, we start with a classical computer, the bit transistor. It's in state 0 or state 1. It has a voltage or it doesn't. And these are discrete states. And the measurement is deterministic. These transistors are almost perfect. So if you set it in state 1, you'll measure it in state 1. Set it in state 0, you'll measure it in state 0. That's all there is to the world. But quantum computers are different. They're based on coherent two-state systems. So those have a 0 and a 1, just like a transistor, but they have much more. And the way that we view it is on something called the Bloch sphere, or you can think of it as the planet Earth, where the north pole is 0 and the south pole is 1. And if you're at the north or south pole, you're just a classical device like a transistor. But these qubits can be anywhere on the surface of the planet Earth, not just the north and south pole. And when they're anywhere other than the north and south pole, they're in a weighted superposition of 0 and 1 simultaneously. This is manifestly quantum mechanical. It's a superposition state, and it has consequences. One of which is if you're standing on the equator, so equally weighted 0 and 1, and you make a measurement, half of the time you'll get a 0, half of the time you'll get a 1. It's one of the purest forms of randomness that we know of. And so what it means is that quantum computers rely on encoding information in a fundamentally different way. Okay, so what is the consequence of that for computing? Well, we can again think of a classical computer, and if you have n, a number n, could be a large number, could be a small number, of these transistors, you actually have an exponentially large number of states you can represent, 2 to the nth power. But you can only represent one of them at a time. So if n is equal to 3, 2 to the third is 8. There are 8 different ways that I can arrange the 0s and 1s, shown here. And if I wanted to process each one of them, I basically have 2 choices. I can either take one computer and I can feed them in one at a time. I get 0, 0, 0 in, I get some function of that out. I feed in 0, 0, 1, I get some function out, etc., and do it serially in time. Or I can buy a lot of computers, 8 of them in this case, and run them in parallel. Either way, if I have an exponentially large number, 2 to the n, of the states that I want to work with, I either need exponential time or exponential hardware to run through them all. Now, quantum computers, similarly, you can have n of these qubits, and you can represent 2 to the n components. So there's an exponentially large number of components, but you can represent all of them in a single superposition state, also with weightings. And what this leads to is a quantum version of parallelism, and also relies on quantum interference, which I won't get into today, but this allows us to process information with much more efficiency. Okay, great. So how do we take advantage of this type of hardware? Well, we run algorithms. And what I'm showing here is a table, and I won't talk through the whole table, but what you see on the left are the categories of algorithms. You'll see on the bottom, most of the folks here at MIT who either invented them or had a strong hand in inventing them. And then these 2 columns are the time it would take on a classical computer and a time it would take on a quantum computer. And the main feature you see is that for all of these applications, n, which started upstairs, comes downstairs, and that means you have an exponential improvement. Not on all of them, but on many of them. And the ones that relate to most strongly, I believe, to the Department of Transportation would be in the quantum simulation area, quantum chemistry, materials, simulating these materials with greater accuracy, for example, and then using those materials to effect for a DOT application. Linear systems of equations, we sample solutions to this linear system of equations using a quantum computer. And maybe most importantly is optimization. Everybody has something that they're trying to optimize, and quantum computers can afford speed up for optimization problems. Now, there's a question mark here in terms of how much speed up you get, and that's largely because there are lots of ways to answer an optimization problem. Are you looking for the one optimal solution, or is a high quality solution good enough? Maybe not optimal, but close enough. And then the question is, how close is close enough? So it's not necessarily clear how much advantage you get on a quantum computer versus a classical, but people are working on that problem. Now, we don't experience exponential growth every day, and so I have here just a simple example of exponential growth. And it's related to, let's say, you may have heard this. Your boss comes to you and says, I'm going to pay you this month in a different way than usual. I'm going to pay you in pennies. And the way that it works is on the first day, you'll earn 2 pennies. That's 2 to the first power. And on the second day, you'll earn 2 squared pennies. That's 4. And on the third day, 2 cubed pennies. That's 8, etc. And then after 31 days, you can either keep all the pennies or you can take a fixed $10 million. Okay, and most of us would sit here, and including myself, say, okay, on the third day it's 8, and on the fourth day that's 16, 32, 64. At the end of the first week, I only have $1.28, right? You could continue on that, and you'd probably figure that, well, it's not going to grow that much. I'll take the $10 million, but that would actually be wrong. On just the 31st day, you would have more than $21 million in pennies just on that day, and this is exemplary of exponential growth. Another way to look at this exponential power is to consider how large a classical computer would I need to simulate a quantum computer. And in particular, how large a classical memory would I need to store all of the coefficients in that large quantum superposition state. So if I have a quantum computer with just 30 qubits, 30, I would need basically a laptop worth of memory and computing power to simulate it. If I increase that to just 50 qubits, now I need a top 500 supercomputer. Go to 80 qubits, and now somehow I need to network all of the computers on Earth with all of their memory just to store the coefficients. Go to 160 qubits, and now I need all of the silicon atoms on Earth, and each one of those atoms somehow is going to be a memory element in this fictitious computer. Now go to 300 qubits, just a factor 10 larger, and I need all of the atoms in the known universe to be a memory element. Okay, just mind-boggling, right? It's another way to think about exponential growth. Sounds great. Why don't we have commercial scale quantum computers today? And it comes down to 2 times. One is called the coherence time, and the other is the gate time. So we'll start with coherence time. That's how long a qubit can retain this quantum superposition state, or its lifetime. So we can start with our qubit or quantum computer in a known state. Let's call it psi. Let's say we can produce that perfectly. From time t equals 0, when I created that, going forward, it's immediately interacting with its environment. Now, it's also interacting with me. I'm trying to run an algorithm on it, but at the same time, unbeknownst to me, or in a way that's not known to me, it's also reacting with its thermal environment, its electromagnetic environment. Any disturbance is also disturbing that quantum state. And over time, the state decays or blurs, and eventually it's lost. Now, the qubits are still there, but they went to some state that I'm not aware of, even though I'm trying to run an algorithm. I'm trying to take them to point state A, and they instead went to some unknown other state B. You know, and that time frame over which that happens is called the coherence time. The second time we care about is the gate time, which is how fast can I apply the operations of my algorithm. You can think of that as like a clock speed in your conventional computers. And the figure of merit is how many gates can I apply before this qubit blurs away. And of course, more gates per coherence time is better. I want to emphasize that we often hear of technologies that have really long coherence times, and that's good, but it's not sufficient. Remember, it's also the number of gates that I can run within that coherence time. And the reason that it's important is that sometimes technologies have long coherence times because they basically just plug their ears to the noise. They just don't listen to it. And often that means they don't listen to me either as I try to run the algorithm. And so the rate at which I can run an algorithm slows down on technologies that have long coherence time. So really the metric you care about is how many gates in a coherence time. And if you think about that number, it's plotted here on the vertical axis on the left. It's number of operations before an error. That's 1-to-1 in the gate fidelity, which is on the right. So if I have one error in 100, that's 99% fidelity. 1 in 1,000, that's 3 nines, etc. And the horizontal axis, well, that's the gate speed. That's how fast I can apply my gates. And so the best performance is you have high gate speed, high gate fidelity in the upper right corner. And what I list here are the different technologies, leading technologies today, and they're where they fall on this plot for 1-qubit gates and 2-qubit gates. These are the two types of gates you need to run arbitrary quantum algorithms. Okay. And so one of the leaders today are trapped ions. So this is a natural atom. In fact, it's an ion. You rip an electron off and you trap it and you hold it and then you operate on it. And here are some colleagues, Ike, Rajiv, and John, who are implementing that technology here at MIT and MIT's Lincoln Lab. The other leader are superconducting qubits. That's my own research area, along with Kevin, Terry, and Jamie. And you can see that in some sense, we're both equally far from the upper right corner, which is why there's no clear winner yet today. Both of us are trying to either improve our gates or make them faster. Now, neutral atoms is another technology, and here's Vladan, Wolfgang, and Martin, who are researching those at MIT, and they've improved a lot over the last couple of years. NV centers in Diamond, which is where Paola works, along with Dirk and Danielle, they can be used for qubits, but they really shine as sensors, and we may hear more about that. And silicon quantum dots, this is probably the closest to silicon technology that we have in quantum computing. And I also do some research in this area in my group. So lots of different candidates being studied here at MIT and worldwide. And which one is going to be the quantum computer? I think it will unfold over time, and it may be both application specific and it may evolve in time, very likely. Okay, so this is what these computers look like today. In the lower right is one of IBM's quantum computers, the Osprey. You can see that it's 3D integrated. This is superconducting. Here's Google's Sycamore chip, which demonstrated quantum advantage a few years ago. That's also superconducting. In the upper middle is Quera's neutral atom quantum computer. And you can kind of just peek inside and see a lot of optics. There's not much to see here. Even less to see on IonQ. This is a trapped ion quantum computer, and all the optics are inside. They hide it here. In the lower right is a D-wave quantum annealer, which is a type of quantum computer, different than the other ones. Again, in a big black box, but it's also based on superconductors. And in the lower middle here, this, of course, is not a quantum computer. You'll likely recognize this as the Wright Flyer. And I put this picture here because I believe that the quantum computers we have today are basically at this stage. When the Wright Flyer flew, it wasn't the first time that mankind took to the air. We had hot air balloons, we had gliders, but this was the first time that it all came together, that a person could get on a plane, steer it, self-propelled. And we knew that when this happened, okay, within some period of time, 10, 20, 30 years, that commercial aviation would come. And I believe that we know that now with quantum computers. But to realize the promise, we need to engineer quantum systems that are robust, reproducible, extensible. We basically need to make a jet airliner and not try to fly on the Wright Flyer. And to do that, I'm coming to the end now, it's going to require something called active quantum error correction. And what I mean by that is the physical qubits we have today, we've worked very hard to get their error rates down to maybe 1 in 1,000 or 1 in 10,000. So 1 error per 10,000 gates. But what we need to reach in order for practical applications is more like 1 in a billion or 1 in a trillion. And there's a giant chasm here. CMOS transistors, by the way, work so well because their error rate is about 1 in 10 to the 20. We don't need to be that good, fortunately, but we do need a substantial improvement. And the way that we do it is not just by improving the physical qubits, but basically by forming teams of qubits that we call a logical qubit. So just like human beings will form teams to outperform any individual, qubits can also be formed or grouped together into teams that we call logical qubits that have better performance. And even though that costs us a little bit, represented by this formula as a C, there's some cost to adding more people together or more qubits together and operating them. The advantage that we get in green is exponential. And so by just increasing the team size from, say, 3 to 5 on a side offers us exponential improvement. And what you can see on this plot that I just showed on the upper right, the error rate per cycle, which means the error rate, basically 1 part in 10 to the 3 is where we are now, is 10 to the 6 or even lower. But the physical error rate is something like 0.1%. So 1 in 1,000. So even with that level of error rate, as we make the team larger and larger and larger, more qubits together, we drive down the logical error rate. And Google Quantum AI has demonstrated improved performance going from, say, a distance 3 team to a distance 5 team, as well as other demonstrations by other groups worldwide, not just in superconducting qubits, but in natural atomic systems as well. And this is what we need to do to reach commercial viability. So, few takeaways. Today's reality with quantum computers. First off, quantum computers aren't going to replace classical computers. For the one reason is that quantum computers don't solve any problem efficiency. They only solve certain problems efficiently. And second is that when you operate a quantum computer, to interface with it, you need a classical computer. So classical computers aren't going away. Another thing is we need more quantum algorithms. I showed a few categories, but what we need are companies or US government to focus on specific problems, like problems that the Department of Transportation has, and take the existing generic algorithms we have and make them specific so we know, okay, how large a quantum computer will I need? How many qubits? What's the advantage over classical computing? Quantum computers do break encryption through Shor's algorithm, but it's not going to happen soon. To break encryption that we use today, we would need around 4,000 error-corrected qubits. That's 4,000 teams, and each team would need about 1,000 people. So we're talking about millions and millions of qubits. So that's not going to happen soon. But we don't want to wait until that quantum computer comes, because we have information today that we need to secure. And that's why we need to switch to post-quantum crypto systems as soon as possible. And I expect that NIST will announce a standard this year. And then the last one is that we'll likely need quantum error correction to achieve commercial viability. Last point is I'm the director of the Center for Quantum Engineering, and we're part of Quantum at MIT that Paola is the director of. Quantum at MIT covers all quantum activities at MIT, and the Center for Quantum Engineering focuses on using these technologies for quantum computing, quantum sensing, and the like. So the mission is the pursuit and practice of quantum science and engineering for practical application and benefit. Our goal is to define this engineering, educate tomorrow's quantum engineers, and importantly, partner with industry and with government to make it happen. And so our membership is we've got 75 PIs, a large industry and US government membership group. We would love to have the Department of Energy or Department of Transportation join us. Contact me, please, if you'd like more information. And so the takeaway message is Quantum 2.0 is going to impact our future information and economic security. There's a lot of promise, still the early days. It's good to get started now. We need a quantum aware workforce. So kudos to the DOT for starting that process. We can help. We have professional development courses. Contact me if you'd like more information on those. And it would be great if you could come up with identifying applications that are important to the DOT, start to develop the quantum algorithms that will be used, form pilot teams, identify use cases, and we can help with that. Join us at MIT through the CQE industry membership group, including US government memberships. We can help. And with that, I'll stop sharing and hand it over to Paola. Thank you for your attention.
Yeah, thank you. So Dr. Paola, she focuses on quantum sensors. So what you hear from Dr. Will is really focused on quantum computing, which, as you understand now, some of the timelines and timescales But Dr. Paola Cappellaro, she's a professor for nuclear science and engineering at MIT. She also leads the quantum engineering group, and her focus really is on spin-based quantum information processing and then precision measurements in the solid state. And she's really looking to realize, working on the goals of practical quantum nano devices, sensors, simulators, and to tell you more about the state of these sensors, the near-term applications, what state they're in. Over to Dr. Paola.
Okay, thank you. Hopefully you can see my slides and you can hear me? Yes. Okay, perfect. Okay, yeah, so thank you very much for the invitation to talk about quantum sensors. I just want to jump right in and trying to define what we mean by quantum sensing and why we think that indeed this is a very eventful technology. So what we want to do is either to leverage quantum mechanics to achieve a few goals. So we want to enhance the fundamental accuracy of sensor, but also enable some new regime of measurement which are not possible otherwise. So we really bridge all scales. I think one of the fantastic example of actually a practical impact that quantum sensor can have already had has been in the detection of gravitational waves. But on the flip side, you can also go down to the nanoscale and really exploit the fact that a lot of these sensors are indeed atomic based, really at the nanoscale to reach spatial scales which have not been possible before. So really quantum sensing can affect all parts of the sensing technology. So why are we interested indeed in using quantum system for sensing, and where does their power come from? I think that there was this beautiful image by the DOT describing quantum technology, which is a very famous Schrödinger cat inside the box. And of course, we know that as soon as we open the box, we actually see the cat being either being alive or maybe sleeping. But while it's inside the box, we don't know the state. But it decays down into one or two possible classical states because there is so much interaction between quantum objects and the external environment that really massive objects are very difficult to display quantum properties. This is a problem for Will, who's trying to build a very large quantum computer. But for me, I'm interested in looking at quantum sensing. And that means that my quantum system, my quantum object, are very, very sensitive to any external perturbation. And so that makes them very good quantum sensors. Still, I want to exploit the properties which are really quantum in nature, such as interferences and superposition. And so we still want to live in this in-between regime where we have very strong interaction with the environment, but we keep the quantum properties. And so it is still a common challenge between quantum computer and quantum sensor to really exploit the most fundamental quantum properties, somehow protect the quantum system from the deleterious effect of the environment, but still exploit them in some sense. And of course, we don't use CAT, as you can imagine. So also for sensing, very often we describe what we are doing with things which are inspired by quantum computation. So our quantum bit being 0 and 1 in the same way that we'll describe. And again, we want to use this parallelism and interferences in order to achieve a quantum advantage with respect to classical sensors. So how do these quantum sensors are embodied in many different systems, and what type of sensor we might have? So similar to quantum computing, also here what we have are sort of like old technology that are indeed based on quantum properties, but they do not exploit completely these properties. So for example, you might have had an MRI. And in MRI, what we're looking at are the tiny magnetic dipole associated with spins, typically with just the water inside your brain here or other parts of the body. And of course, spins are quintessential quantum mechanics. You cannot explain them with classical mechanics, but their evolution and their properties as used in MRI, really you could use classical mechanics to exploit them. So this is similar to transistor, where the fundamental properties are quantum, but how we exploit them are basically classical. And so we are nowadays, of course, we still exploit this type of technology. We are not going away. But in order to really push quantum sensing, we are more interested in focusing into other classes of quantum sensors. So the first class is where we use some quantum properties, typically coherence, in order to achieve a regime which are not possible otherwise. So this could be really linking some sensor to fundamental property of physics, like, for example, the energy level of atoms, which are set by nature and very precise and immutable. Or we can exploit the fact that we're really at the nanoscale, and so we can bridge this spatial resolution, which is not possible with a bulkier classical sensor. The other type of class of quantum sensor that we are interested in are instead sensors where we are really trying to achieve a so-called quantum advantage in the same way that we'll describe this exponential improvement in performance that quantum computer can have over classical sensor. Similarly here, for quantum sensing, we will have it's a more modest polynomial advantage with respect to classical sensor, but nonetheless, this can really give rise, if you want, to improve performance. And this relies on really even weirder quantum properties, such as entanglement, so quantum correlation, which are not found classically. In both two cases, as I say, we still want to achieve performances which are better than overall quantum classical sensors. But in some sense, how we do the sensing itself is sort of similar to what you will have with classical devices, up to some, again, differences which arise from the property of quantum mechanics. So again, you will have a sensor, you will initialize it, but in the same way that we'll describe, you do not initialize your sensor in one specific state. Typically, what you want to do is to have a superposition of possible states, because this allows you to exploit interferences and improve your measurement. Then you will let your sensor evolve, or if you want, you put it in contact with whatever you want to measure, and this will, of course, change its state. Again, this relies on the fact that the quantum objects are very sensitive to external perturbances, and we exploit that to induce and change in their state. Then we will perform a measurement. And here again, quantum mechanics sort of changes a little bit things, because the result of a measurement is random in nature because of the law of quantum mechanics. So we need to repeat this many times in order to accumulate enough statistics to actually be able to say something about what the measurement is. This sounds, of course, both weird because the randomness is introduced for quantum mechanics, but also very familiar, because even if you have a classical instrument, you will still have some errors and if you want randomness in the measurement outcome, which will lead you to repeat the measurement many times. The source of randomness are of course different, but if you want, the end result is sort of like similar. And then from the measurement that we will be able to estimate the parameters that we are interested, which was giving rise to a change in the system. So all these steps are sort of like very common to classical and quantum devices, but again, we were twist for quantum devices. So again, we have like just three simple steps: initialize, evolve, and measurement. And how does that sort of look for one particular instance of this? So one of the most common schemes which are used for sensing is the so-called Ramsey scheme, which is really just one way of doing interferometry. And you can do that with light, with matter sensor, with atoms. And the three steps are really common, and you don't need to, you're welcome to go through the math if you're interested, but really the understanding is to prepare in a superposition state, let the system evolve, and this will lead to the appearance of a phase interference, and then you measure out the outcome. And how does that look, for example, for a spin, which is the system that I typically use? Well, you will have some external magnetic field, which will induce a change in the energy, this H for my spin system in the Z direction, and this will lead to a precession of the spin in this Bloch sphere that we'll already introduce. So this is very similar to have, if you want, the compass needle move around and rotate in the presence of a magnetic field. And we can sort of map the sensing like protocol, which if you want is a sensing algorithm, into a real operation that we will do on our system. So rotate the system around the x-axis, let it evolve for some time, and then rotate it back so that we can measure out things. So where does the, if you want, the advantage in quantum sensing arise? As I said, if we have one single sensor, we do one measurement, the measurement outcome will be random. So we will need to repeat it many times. Or maybe we have many sensors and we measure them all at the same time. Typically, this will allow us to reduce the uncertainty with which we measure our parameter, in this case, for example, a magnetic field. And this uncertainty will decrease with the number of sensors that we have, and also, if you want, the number of times that we repeat, so with time. However, if I'm able to create a quantum state, for example, the so-called cat state, so a little Schrödinger cat now, for example, with atoms or with photons, we are able to achieve a sensitivity, or if you want an uncertainty, with decrease better, with a scaling which is better in the number of sensors than the classical one. So we have an improvement which is proportional to square root of n. So this is similar to the quantum advantage, except for quantum computer, this can be up to the level of exponential. For sensing is a more modest advantage. It's just a polynomial, but still it gives rise to, let's say, practical success, if you want. At the same time, we can let the system sort of be affected by noise more strongly than quantum computer, and so we have a better compromise between, if you want, noise and sensitivity. In terms of technology and system that we have, for sensing, there is a really a large variety of potential implementation. And while, again, for quantum computing, maybe at the end we will have a well-defined winner, like one technology which will result to be the best one for overall quantum computing. I think that for quantum sensing, we will never have that. And just because basically we have so many different sensing tasks, and so different like experimental system might end up being better than for one particular task with respect to the another one. So for example, we have spins which are very sensitive to magnetic field, and so they will be good magnetometers, while maybe atoms are better at detecting detecting time, and so they're the basis for atomic clock. So different tasks will need different implementation. So I think that it's very good to sort of like push for all the possible platform at the same time. And of course, this goes hand in hand also with improving the control and the precision of application that we will need for quantum computation. So the two fields are really interconnected. So here I have a table of some of the potential implementation. And I don't want to go through all the table, but just give you a flavor of a few of the potential application and implementation that we have, starting with atoms. And I want to start with atoms because these are actually one of the, if you want, the oldest quantum technology for sensing. And I mentioned these different quantum like sensor of the zero type and the sensors which are more advanced. And if you want, atomic clock are sort of in between where, of course, they have already been used and they are the basis for GPS, but people are keeping pushing their performance. And they're adding some additional quantum logic, like, for example, error correction. They're adding entanglement to have better performance, and really pushing it to the extreme level. So I have to keep updating this slide. So this slide, as you can imagine.
Oh, so two more minutes, Paola.
Yeah.
And then we can
So,
get to the Q&A.
I have to keep updating this slide. So that, like every year, I need to decrease this number. So this is the latest number that I have. And it has reached the level where people are able to measure, in this case, neutron atom, 1 millimeter apart, and test general relativity. So you might know that there is time dilation. So if you're sort of like very far apart at times, if you want to travel at different speed, but if you're able to measure differences time with absolute precision, then this distance can be reduced down to 1 millimeter. And that's what we've done 2 years ago. As I said, you also can have a quantum advantage in sensing. So if you use entanglement correlation, you're able to reduce the fundamental limit of sensing. So here is what is being demonstrated at MIT by using entanglement in atoms, where we're able to take the classical level of noise and reduce it down and achieve this 4.4 dB of improvement by using, in this case, squeezing, which is indeed a form of entanglement. And of course, this atomic vapor has also been used for inertial measurement, where in this case, like the effect of acceleration, rotation, for example, also gravity, changes, if you want, the path of the evolution of the atoms, and through the interference, one is able to estimate acceleration, rotation, and so on and so forth. Another modality, which is indeed the one that I typically work on, sort of takes its inspiration from NMR and MRI, which has been around for a long time, but push it forward, going toward, if you want, higher precision and higher spatial resolution. This is based, at least one of the implementation, which is the most common, is based on electronic spin defects in diamond, called nitrogen vacancy center, which are a nitrogen close to a vacancy in the diamond lattice. And these are color center, meaning that we can see them, we can see individual electronic spin by using laser light. And so these are, for example, images of a few of them in our lattice. And we can use that and use at the same time the spin properties to see magnetic field. In this case, a resonant microwave control, sort of bring my qubit sensor from up to down and periodically, and so I can detect indeed what is the magnetic field that we can that has been applied. And this has a lot of application, including, of course, navigation, both in the terms of a spin gyroscope or by detecting the like the Earth magnetic anomaly detection, which allows the GPS-denied navigation. But it can also be used in condensed matter and also in chemistry to find properties of biological and other molecules, in detecting properties of materials, for example, in high pressure and with nanoscale precision in 2D materials, and so on and so forth. So I think that I'm running a bit out of time, so I'll skip ahead of some of these, but I'm happy to answer questions about any of these applications. So as I said, we can use the nuclear spin associated with NV center in diamonds to devise a rotation sensor, which we think can be more stable than a current one and potentially combined with MEMS for robust sensing. We can use the fact that magnetic field can be sensed with very accurate precision down to the picotesla and lower in order to indeed detect variation in the magnetic field of Earth. And so from that and the mapping of these anomalies determine where we are navigating. And of course, we can use that for also sensing of materials and to help discover new material through their chemical properties. There are, of course, a lot of startups already working in this area, and these are just some of them. There are quite a few which are based on atomic clock and atom interferometer for navigation, and a few which are instead based on these spin defects in diamond and in other materials, including, if you want, established companies that have developed their own in-house startups in order to take advantage of these new technologies. Of course, there are challenges, but also I think many opportunities, and these are really my last slide, with which I want to leave it to you. So in the same way that I will mention, so coherence time, so how long your quantum sensor survives with its quantum property intact is very, very important. And as I said, the challenge is a bit less for sensors. We can live with a bit more noise than the 10 to the minus 10 noise level that Will was saying. But we also want this sensor to be out in the field. We don't want them inside these black boxes that quantum computers are. They should be close to surfaces, that should be in right condition. So in some sense, even if we can live with more noise, we do have more noise which are present. We, of course, want to sort of like improve the integration and miniaturize the sensor so that they can really be portable and be deployed. We would like, of course, to exploit this quantum advantage. Many of the current sensors which are out in the field, they do not exploit yet the quantum advantage, but exploit this link to fundamental constant, with spatial resolution, but maybe not the quantum advantage. So this will bring additional, of course, opportunities. And then, of course, we are always looking for new application and new sensing target. For example, one would be to integrate with quantum computer, use sensor to detect the state of quantum computer in a better way, and also translating to commercialization. So I'm happy, of course, to talk about any of these, and here my email for potential follow-ups. Thank you.
Amazing. Thank you, Paola. This was so great. So I invite now Dan and I, maybe we can take a few questions. And if you have some time, maybe we might even go over but let's start to get to the key questions. The goal here, by the way, for everyone on the call was really to give you a good theoretical understanding of where quantum computing and sensing is. And in the workshop, we're hoping to dive much deeper. So that workshop is July 10th. Put it on your calendar. We'll send you the links again. But there we'll go much deeper into it, but also we'll be inviting companies that are deploying and developing these sensors that have computing. At least they have ways for us to get started, and it'll be much more hands-on. But the goal here was really introductions, and I think many of the questions I see, cost, how does it compare, we'll really get to in the workshop. Maybe first question, and then Dan, I'll hand it off to you. From Charles Tapp, I think this is a good question, is like, can quantum tech replace fiber optic communication? Or quantum entangled communication.
I'm sorry, could you repeat that? Can quantum tech do what?
Yeah, can quantum technologies replace fiber optic communication?
Well, there is a type of communication called quantum communication or quantum key distribution. And it, in fact, can use free space communication, or it can leverage fiber optics to convey photons back and forth. Here at MIT, we do have a underground fiber that runs between our campus and MIT Lincoln Lab, also to Harvard. And we've done experiments to show that this quantum key distribution can work over, fiber that's already in the ground. The issue is that, there's a small amount of loss of photons for every kilometer that it travels. And currently, roughly at a metropolitan scale of maybe 50 kilometers, 100 kilometers, that's about the limit before you lose too many photons. So quantum key distribution over that local area works okay. But if you want to go longer distance, you have to make a quantum version of a repeater. Now, if you use free space communication, you can communicate a bit longer distance. So people have demonstrated going up to a satellite, then from one satellite to another, and then back down to Earth. So that's another way to do it.
Thank you.
Okay, well, thank you. I'll hop to the top of the list of the questions. There were a couple early, Will, I think these are both for you, a couple early questions related to AI. First question is what you think the impact of quantum computing will be on current AI applications. And then the second question, I'll paraphrase, it seems to be asking, where is there a role for AI in the optimization of quantum error correction? So if you want to take both of those. Yeah,
just short answers here. The second one, absolutely. Using conventional classical AI, we're already starting to do that. Machine learning to make the optimization of our quantum systems better, faster, easier, absolutely. The use of quantum computers for AI, it's still at an early stage. People like Seth Lloyd have developed algorithms that could do principal component analysis, for example, which is a part of learning. There may be ways to train neural networks using quantum computers in tandem with classical computers, but that still has to be developed. It's easy to say in words, but What I really want to see as a scientist is show me the algorithm that's going to do it, show me the use case, and actually let's turn the crank and see it happen. So I would love to see that.
And Will, if I may, I'll add one thing that we have just started talking about. One of my colleagues, sort of an intersection of different HASS activities. One of my colleagues is very deep in AI assurance, and we're starting to wonder, is there an opportunity here? So not for quantum computers to run the AI, but for quantum computers to evaluate the performance of AI in terms of predictability, reliability, and things like that.
Interesting. Yep.
Prachi, do you want to take the next one, or do you want me to go down the list?
You can go down, please.
Okay, let's see. Next we have from Matt Cuddy. Knowing that this is hard to estimate, how many years in the future do you expect the first practical applications of quantum computing? And let's make that a question. Let's make that a question for both. When do we expect to see, I don't know, quantum sensor-based navigation or something like that? So we'll ask it both in terms of quantum computing and quantum sensing.
Hey, Paula, why don't you go first?
Because it's a hard question to answer. Yeah, I mean, I think that, as I say, there are already a few startups which are indeed providing their services for navigation based on, especially with inertial, like atomic vapor inertial sensors. My understanding is that, they're still working on making it more practical, meaning that the performances are sort of there, but the package is large. So, you need to reduce a little bit the package to really making really competitive, and that's part of the problem. Timeline, it's accelerating. So it's I think that I'm actually very optimistic.
Yeah, and on the computing side, I often throw the question back and say, when did we have a classical computer? What date was that? And people struggle a bit because we know that classical computers evolved over time, right? We didn't have an iPhone in 1950. It took a long time to get to that point. And quantum computers, similarly, there are small-scale quantum computers in the cloud. You can use them to test algorithms. They're not of a commercial scale yet. They will get more and more powerful over time. Something to keep an eye on is quantum error correction. When does that drive down the error rates to levels that we can, in principle, do commercial scale algorithms? It's like 1 in a billion or 1 in a trillion. That's something to keep an eye out for. But these quantum computers are going to get more and more powerful, and people will figure out ways to use them. Timeline, I'm guessing 10 years, something like that.
All right, wonderful. Thank you. Prachi, would you like me to keep going? I know we're at time, or do you want me to?
Yeah, Will and Paula, do you have maybe a couple more minutes? We can keep going.
Sure.
Okay, great. Okay, please.
Okay. So there's a comment from Mr. Sims from the FAA. Suggestions on how we might use quantum technology for transportation. Let's bring this to the workshop. This is exactly what we want to see when we get together in person in a few weeks. And then skipping down to Michael Watkins, also from the FAA. I can think of uses of technology for aviation, some initial use cases for transportation under consideration at MIT. And maybe to help the question along, I'll even say both on the sensing and the computing side. Is there in terms of chemistry of materials, is there, in terms of battery chemistry, I don't know, roadway chemistry, anything you like? Can you think of applications that we might apply quantum computer and quantum sensing? In the sensing example, the mining scanner with the truck driving along, I think that very suggestive of the infrastructure application. So I'll hand it over to you.
Yeah, please go ahead, Paula.
Yeah, so I think that indeed there are what we as faculty at MIT can think of application to navigation. And to me, it's very much like the GPS denied scenarios where like because like it seems that otherwise, beside improving atomic clock, we already have a good infrastructure. But indeed, what we want to do is to sort of exploit the fact that you have these sensors which are like really linked to fundamental quantities, and so you're able to sort of like have a more robust sensor over time, and that to me is what makes it appealing. But I'm really looking forward to have the input from the expert in telling me, well, okay, yeah, this idea that you're thinking, it's a bit naive in terms of practical application because we have X, Y, and Z. So I think that like it's wonderful to actually. Maybe I don't have a very good answer, but I'm really looking forward to all the input. Like I think the message was like, I can think of 10 scenarios. I'm like, tell me, please.
Yeah, I completely agree with Paola. You know, we sit here at MIT and we, you know, think big thoughts, but the reality is we formed the Center for Quantum Engineering and its industry and government membership group precisely so that we could have these types of interactions, because you're the experts on what's needed for the Department of Transportation and your mission. And, you know, by working together, we can pinpoint some of these use cases, start working through them, see which ones provide advantage, which ones don't, and even test some of them. So I think that, you know, off the top of my head, optimization is probably a big one. Satellite tasking, sensor tasking, you know, airplanes flying into an airport. But these are going to require, you know, very mature quantum computers. We don't want to put people's lives at risk on the quantum computers we have today. But one can foresee these types of applications in the future. And then there's the more generic, if I could build a better material, maybe I could build a better road, right? But that's a second order. First, you simulate some materials, then an engineer uses those materials to make better asphalt, right? So that's another potential application of quantum computers, but second order.
Okay. Yeah, I will. We'll stop there. I will make sure that I get all the rest of these questions in my notes, and we'll get you an answer. And we want you to be at the workshop to get these answers and help us develop them further. You heard from both of our guests. These are the experts and their interest in our applications. Let's not let this opportunity go. So thank you both, Prachi, Stephen. I'll turn it back over to you.
I'll do a plug for the workshop. So, you know, Will and Paula, they really set the foundation, and the workshop will be a day long. We'll start at 9 in the morning. And the goal is the first half, not only hear from the computing and sensing experts, but we'll have startups come there as well. We'll have folks from DoD and ARPA who've been working on these sensors for a long time tell us what's currently available. And then the second half of the workshop, it's really bringing the transportation and the quantum people together and starting to look at use cases, you know, for X use case, should we even use a quantum computer? What type, what maturity levels, what are some of the requirements for sensors that we have in our sector? So this should be really exciting. As Dan said, let's not let this opportunity go. And I look forward to seeing all of you on the 10th then. It's in person at the DOT.
Wonderful. Well, lots of unanswered questions here, but I think one question we have answered for sure. One thing that we're certain of is that it's a little bit late. So thank you all for your attention. Thank you especially to our moderators and to our experts, Prachi, Dan, Will, and Paola, for this really thought-provoking conversation. And thank you everybody in attendance for joining us today. As Prachi said, look forward for an invitation to our in-person workshop later this summer, and wish you a wonderful day. Thank you, everybody.
Thank you.
Thank you.
Bye-bye.